Okay, so this is the first video for section 7.2, where we start to investigate confidence intervals in general. So why don't you pause, copy this panel down, press play. All right, so in section 7.1, we focused on finding confidence intervals for parameters where the data came or looked like it came from something normal, a normal distribution. So in general, we're now thinking about, well, what if the data comes from a distribution that's not normal, okay? All right, so our setup is we've got a random sample x1 through xn. It's a random sample from some distribution, and that distribution has an unknown parameter. Let's just call it theta, all right? So with the normal distribution, the two parameters were mu and theta. Mu told us the mean, theta squared told us the variance, but those were the two parameters that maybe we knew, maybe we didn't. So now in general, we've got a distribution with at least one unknown parameter, theta. And our goal is to find a confidence interval for theta, given a random sample from the distribution, okay? Now, in particular, let's define what we mean by a confidence interval here. In particular, we want to find values capital L and capital U such that theta is greater than or equal to L and less than or equal to U. I'd like the probability that theta lands between L and U to be 1 minus alpha. So maybe alpha is 5% if I wanted a 95% confidence interval, okay? And then I would like this distribution to have alpha over 2 probability below L and above U. So I'd like the confidence interval to have as much probability to the left of it as to the right of it, right? Doesn't mean it's symmetric about the mean. It just means there's an equal probability on either extreme, beyond either extreme of the confidence interval. Okay. All right. If we can find that L and that U, we say it's a 1 minus alpha times 100% confidence interval of theta. So we have found these, right? In section 7.1, L, for example, could be the sample mean minus 1.96 times sigma over square root of n. And that's if the data have been normally distributed and we happen to know sigma. So that was technique 1 in section 7.1. Okay. So now we're just generalizing this idea. So the way we're going to find our L and our U in general is to use something called a pivot. Now, a pivot is a random variable. It depends on the data and the unknown parameter. Okay. But the distribution of the pivot does not depend on that unknown parameter. All right, I will illustrate because it's maybe slightly not clear why that would be of use. Okay. By the way, there are 4 panels to this video. All right, so pause, copy, play. Okay, so let's look at an example we're familiar with. So we'll go back to the normal land. So let's say I've got some data from a normal distribution with mean mu and variance sigma squared. And let's suppose that sigma is known. So this is, again, situation 1 from section 7.1. Now, if you remember, in that process of getting a confidence interval for mu, I created this random variable, sample mean minus unknown population mean, all over sigma divided by root n. All right, this is a random variable. It varies with the data. It contains the unknown parameter mu, and its distribution is n01. And look, that distribution doesn't require mu. It doesn't depend on mu. So this random variable over here is a pivot. It depends on the data to get x bar and the unknown parameter mu, but its distribution does not depend on mu. All right. So we're just going to generalize this to the non-normal. So let's look at an example, a couple of examples to finish off this first video. So suppose I've got a random sample x1 through xn from an exponential distribution with unknown parameter lambda, okay? In Math 313, we learned that the sum of exponentials is a gamma distribution. So it's gamma n comma lambda, right? And we also knew that the expected value of each one of these x sub i's was the mean of the exponential distribution, which was 1 over lambda, which we often called theta, right? And if you recall, lambda came from a waiting time in a Poisson process. So, okay. All right, well, it can be shown that if I take the sum of these random variables and multiply by lambda, that this new random variable is gamma n comma 1. By multiplying by lambda, I scale down the second parameter down to 1, okay? Now, note, this new random variable, it depends on lambda, but its distribution does not depend on lambda. So this new random variable, lambda times the sum of my data, that's a pivot. And we can use it to find a confidence interval for lambda, okay? Now, we don't have to go through the gory details of why this is gamma distribution, but we would have just used the distribution technique that we learned in Math 313, which I'll remind you of again in the next couple panels over. All right, so we've got this idea of creating a pivot with exponential data, and what's enacted on this panel here. So pause, copy, play. All right, so now here's some data. 2, 2.5, 3, 4, 9. So there's a random sample, and it all came from this exponential distribution whose lambda I don't know. But I would like a 95% confidence interval for lambda, all right? Well, clearly n is 5 data points, and the sum of my xi's is 20.5. And from that previous panel, I know that lambda times the sum of the random variables is distributed via a gamma 5, 1 distribution, okay? So I went to R and I asked, what's the 0.025 and the 0.975 quantile of this gamma distribution, okay? And it turned out it was 1.6235 for the 0.025 and 10.2415 for the 0.975, okay? That means that 95% of the area of this gamma distribution are between the 1.6 and the 10.2. And we know this monstrosity in the middle follows the gamma 5-1 distribution. So I get this line. And now I'm simply going to solve for lambda because that's what I want the confidence interval of. So x1 up through x5 added together is 20.5. I can divide all three portions by 20.5 and simplify. And so I've now figured out that 95% of the area, 95% of the time, lambda is between 0.079 and 0.4996. Okay, it's not quite what I figured out because it's the old, what does a confidence interval actually tell us? But I have this as a 95% confidence interval for lambda. That means if I take 100 random samples of size 5 from this exponential distribution and make a confidence interval for each one of those 100 random samples, that 95% of those 100 confidence intervals should contain the true value of lambda. Cool. So I created a pivot variable. Its distribution did not depend on lambda. So I could get my quantiles, set it into a probability equation, and then solve for lambda to get lambda's confidence interval. Now, something to note. 1 over lambda, we often called theta, and that was the mean of the exponential distribution. And so one great way to estimate the mean is to just do the sample mean. We know that's an unbiased estimator. So I could approximate 1 over lambda by x bar, and thus lambda would be approximately 1 over x bar, which is 0.244, okay? And the only reason I bring this up is this confidence interval is not symmetric about our estimator of lambda, okay? That confidence interval is lambda minus 0.165 and lambda hat plus 0.256. So it's not symmetric about the estimator. And this should make sense because, heck, the distribution, the exponential distribution, is not symmetric about its mean. So why would you expect the confidence intervals to be symmetric about their estimator, okay? All right, so we do not need confidence intervals to be symmetric about the estimator. Now, in the normal case in section 7.1, it was, but that makes sense because the normal distribution and the student t distribution is symmetric about their means. Okay. All right, last panel. Okay, so pause, copy, and play. All right, so now I'm going to look at the scenario where we have a single observation from an exponential distribution. I don't happen to know lambda. I'll remind you of the PDF of an exponential. I'd like to find a 95% confidence interval for that lambda. Okay, well, since x1 is exponential lambda, that means that lambda times x1 is exponential with a mean 1. And we could figure that out using the distribution technique from Math 313, all right? So that's where we look at the CDF of this new variable we've created. And we create the CDF, and then we take the derivative to create the PDF, and we look at that PDF and say, oh, hey, look, that's an exponential, okay? And the parameter happened to be 1. So we could go through the Math 313 technique to figure this statement out. Anyway, though, if you know lambda times x1 is a random variable, depends on x1, but its distribution does not depend on lambda. So that's a pivot, okay? So I'm going to find the quantiles for this distribution. So here's the 0.025 quantile. It goes from 0 to Q1, integrating the PDF of that distribution. So there's my lambda e to negative lambda y, because lambda is 1 here. I can solve, crank it out, do some algebra, and I get the first quantile is 0.0253. Get the 97.5 quantile doing the same idea. Solve for that quantile as 3.689. And that tells me that there's a 95% chance, the probability that lambda times x1 landing between the two quantiles of lambda times x1 landing between the two quantiles, okay? So I set that probability statement up. This is my random variable depending on lambda, but its distribution does not depend on lambda. Okay, so I can set up that probability equation, divide both sides by x1, and there's my confidence interval, okay? And if you note, if I happen to grab a small value of x1, this confidence interval could be pretty darn long or large, right? Which isn't ideal, but that's the way it goes. It should not be a surprise that we might get a really large and unhelpful confidence interval because we only have one data value to base all this. Not much data, you get crappy results.